Welcome back, students and viewers. I am Hussein Yasir Razak from MES College of Arts and Commerce, Zuarinagar, and we are doing Mathematical Economics 1, ECD 117. This is Unit 1, Basic Concepts in Mathematics, and the module that we are going to be doing today is Sets and Set Operations. It's module number 8. In the outline, we have an introduction to set theory, components of a set, representation and notations, set operations, and Venn diagrams. In the learning outcomes, the students will be able to familiarize themselves with set theory, will be able to perform basic set operations, and will also be able to familiarize themselves with the basic Venn diagrams. So, set theory. What is a set? A set is a well-defined and distinct collection of objects. Now, there are two important words that we need to look at here. It's well-defined and distinct. When we say well-defined, what we are saying is that there is a specific criteria to be part of the set, and this criteria could be anything. And when we see a specific example, you will understand it much more better. The second thing we have is distinct, and distinct means that each object in that set is different. In other words, what we are saying is there are no repetitions. Having said that, let us take some examples. The first example here is the days of the week, and we have in this set Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So, let us check if it actually fulfills these two criteria that we had. One was well defined, is it well defined, and second, is it distinct. So, very surely we know it is distinct. There are no repetition in days. Monday is only once, Tuesday is once, Wednesday, Thursday, Friday, Saturday, and Sunday. So, it's definitely distinct. Is it well defined? Yes, it is well defined because it says days of the week. You couldn't be more clearer and more precise. The second example we have here is all the alphabets from A to Z. Now, if you look at this particular example, you have A, B, C, and then you have an ellipsis here that's telling you that there are some number of letters there in between, and then we have again the ending three letters X, Y, Z. So, this is also a set. Is this distinct? Yes, of course. There are no letters repeated in the 26 alphabets that we have in the English language, right? And also it is well defined because we are saying that these are alphabets from A to Z in the English language. So, it is well defined. So, hence these are two examples of set. And it is very interesting to note that a set does not necessarily have to be of numbers. It could be, but it does not necessarily have to be of numbers. It could be any objects. You could go to a restaurant and you could look at their menu and you could make a set out of all the things available in the menu. Okay? The order of the different items in a set does not matter. What matters is that each element is counted only once. It is distinct and the property is specified very clearly. The order of listing the element do not matter, just like I told you a while back. Okay? If you could place Wednesday before Tuesday and Tuesday after Wednesday, there would be absolutely no difference. So, let us now look at what components of a set are. Let us take the same example, all the alphabets from A to Z. In this particular example, we can see that A is the name of the set, usually denoted with capital letters. We know that these curly brackets that you can see are braces, and these tell us that those are the elements which are contained in this particular set. So, these are your braces. We have elements from A to Z. Of course, we all know there are 26 alphabets, but these 26 alphabets cannot be specified in this small area. So, we use these three dots here, which is nothing but ellipses. Okay? What these three dots mean is that there is some unknown number of elements, and it is used to shorten and write a long expression. So, if we had this ellipsis at the end, it means that it would be an extreme infinity situation where we do not know where it ends. If we had it on the extreme left, it would mean that we did not know what is the left extreme. In this case, we have it in between A, B, C and X, Y, Z, because we want to make sure that we say that there are some numbers, but we don't want to write it down now. Okay, that's what the meaning is of ellipsis. And the order of this set is nothing but the number of elements that it contains. So, in this case it is 26. Let us look at the next slide, and a set is nothing but a well defined and distinct collection of elements, right. Hence, these elements may very well be numerical in nature. So, let us look at some numerical sets. The first example, let us say a set of even numbers from 1 to 10, and this set would contain within its braces 2, 4, 6, 8 and 10. If we look at the second example, we have a set of prime numbers from 1 to 20. Again, within the braces we see the elements that 2, 3, 5, 7, 11, 13, 17 and 19. These two cases where you do not see any ellipsis are cases of finite sets, because we can actually enumerate how many elements are there within each one of them. However, the third example, that is a set of odd numbers, you would have started from 1, 3, 5, 7. Pay attention that when I say set of odd numbers, I have not mentioned up till what. Therefore, obviously like any number system, it would go on up till infinity. So, even odd numbers would keep extending up to infinity, right. So, hence we have the ellipsis here, and this is an example of an infinite set to the right positive extreme. Okay. Let us move on. Let us see the different representations of a set that we use. Example, let us take set of all prime numbers less than 10. There are three basic ways of writing down this particular set. The first is the statement form. So, again we would write these statements inside the braces, because that is the way sets notations are written. So, in this statement form also we would write the statement which is nothing but the prime numbers less than 10. That is the criteria, that is the defining criteria. So, in the statement form it is as simple as writing the actual statement within the braces. The second method is the roster form, and in this case we can see that set A is equal to, and it contains the elements 2, 3, 5 and 7. These are the actual elements that come up from the statement that is all prime numbers less than 10, right. So, when we actually note down the elements, we call them the roster form of representing a set. And finally, we have the set builder form, widely used form in mathematics, because this set builder form allows us to write very complex statements in a very short way using set theory. So, in this case we are saying A is equal to a set where x is the variable, and this x variable is being determined by some property. That property is prime numbers less than 10. So, you have the variable and you have the property here, right, and these are the two things that we will mention in a set builder form. Let us move on. Let us take an actual example in economics. Let us talk about the budget set. Look at this particular equation. I know it looks a bit complicated, but we will break it down in a bit. This particular budget set is nothing but a set consisting of variables x and y, as you can see on the screen, and it has certain properties or conditions that you can see here. Okay. So, let us see what these are. X and y are nothing but consumption bundles. They are a pair of quantity of some commodity x and some commodity y. And this whole statement that you saw here, that is p x plus q y less than or equal to m, is basically your budget constraint. P is the price for x, q is the price for y, and it is telling you that when you are going to make this consumption bundle, this choice, you have to make sure that you buy these things at those prices, and it has to be less than or equal to this particular level of income or money that you have. This is your budget constraint. Okay? This is the first constraint. So, from here to here you have the budget constraint. That is the first property that this particular set is defining. Then you have two more things, that is x is greater than or equal to 0 and y is greater than or equal to 0. These are called as non-negative constraints. What are non-negative constraints? Like I have told you before, when we deal with economics, there are certain things that cannot be negative, like quantity of x and y. In this particular case, two commodities cannot be negative. You can't have negative 5 loaves of bread or negative 5 mangoes or negative 10. So, hence these numbers have to be positive. Hence, this particular non-negative constraint which says that the value of x and y has to be greater than or equal to 0. So, these are your properties and these are your variables x and y, because you have two. Hence, this is a set, a budget set, and this x y is nothing but a consumption bundle, and these were the properties just like I have told you. Right. Let us look at some standard notations in sets now. Let us look at the first one. The first one is x belongs to S, where the interpretation is that x is nothing but an element and this element belongs to a set S. Then we have the second one, that is D does not belong to S. The interpretation is that this element does not belong to set S. There is a set S and there is some element D, and this element D does not belong to S. The third one is A is a subset of B and A is not equal to B. The fourth one is also A is a subset of B, but A is equal to B. Notice that the small difference in this particular notations here, there is an equal to sign in the second one. The fifth one is n of A, basically telling you that it is the number of elements present in set A. Next we have the symbol phi, which is basically the symbol for the null set. As you can see, this is the symbol for the null set, okay, and the number of elements in this null set is 0, because there is nothing in that set. At sixth, we have the sign omega, which is nothing but a symbol for universal set. So, what is a universal set? The universal set is a set containing all elements fulfilling the specified properties that we mentioned. Then at number 7, we have complement of A. It is nothing but the complement of set A. These are all the points that are not in A, but are in the universe. Then we have at 8 superset. We say A is a superset of B, but A is not equal to B. And the ninth one is A is a superset of B and A is equal to B. These are some notations that we are going to be using in sets when we move further. Now, we come to set operations. We have three basic operations here. The first one is A union B, the second one is A intersection B, and the third one is A minus B. We will be looking at these closely in the next Venn diagrams. Let us take an example. Assume that you have the following sets: A is equal to 1, 2, 3, 4, 5, B is equal to 2, 3, C is equal to 2, 3 and D is equal to 4. So, if I say 1 belongs to A, yes, I know 1 belongs to A. I say 1 does not belong to B, you can see clearly in B there is no 1 there. You say B is a subset of A, look at B, B is 2 and 3 and 2 and 3 is part of A, therefore, yes, B is a subset of A. B is a subset and B is equal to C. Look at B here, look at C here, exactly the same elements are there, 2 and 3, 2 and 3. Therefore, yes, they are a subset and they are equal. N of A is equal to 5, there are 5 elements here in this. N of B is 2, you can see that N of B is 2, C is also 2. Then we have B union D. So, you have look at B and look at D, and B union D is nothing but the combination of set B and D. So, you have listed down all the elements of B and D. A intersection B, that is nothing but 2, 3. This is telling you that whatever is common between A and B, and you see clearly that 2 and 3 are the numbers that are common in A intersection B, right. These are common between A and B. Then we have A minus B, which means that which are the elements that are there in A, but are not there in B. Now, we know that the common ones were 2 and 3. So, what is left is 1 and 4 and 5. So, that is A minus B in this case. And finally, the last one, C intersection D, that is nothing but a null set, because between C and D there is nothing common. Therefore, the answer will be a null set, that is the symbol phi. And last, let us spend a minute looking at Venn diagram. This is an interesting way of showing us how we can look at a large number of sets in an interesting way. So, you have two sets A and B, A is 1, 2, 3, 4, 5, B is 4, 5, 6, 7. This particular diagram shows you A union B. That means it's a combination of all the elements of A and B without repeating any number twice. So you have 1, 2, 3, 4, 5, 6, 7 elements in A union B, and this shaded part that you can see here is nothing but the representation of A union B. Then we have A intersection B, which is nothing but the common part between them. So you see the common part between them is 4 and 5. Right, 4 and 5, therefore, this will be 4 and 5. Then we have the subset. You see 4 and 5 are here and they are part of A, therefore, we can say that B is a subset of A, and we can say hence that A is a superset of B. Finally, we have a complement, which is all these points that exist in the universe which are not in A, that is a complement. So, this is something for you to do. Take time, get your pen and papers out, solve these, shade the regions that are being asked in this question, and this is the references that you can dwell upon. I will join you again in the next module. Thank you very much. I am Hussain Yasir.